Hello pre-calculus and welcome to another video of notes, this time on properties of logarithms. In our last video, we looked at the logarithmic function and what it looks like on the coordinate plane, and today we're going to be focused on the properties that allow us to manipulate equations that are using exponents and logs. So to begin, we're going to compare our exponent properties with some new log properties. We've already covered exponent properties when we were in school in person, so now we're going to focus on how log properties relate back to those exponent properties. So to start, log properties come from exponent properties in a sense. So in our last video, we confirmed that log base A of n equals m. And so essentially, when we have a log base A, we are searching for the number that could be used as an exponent to produce n. So that's how all those things are related. And notice that the base number here is the same as the base of this logarithm. Okay, we're going to see that very often as we move forward. We had an exponent property where when we multiply two numbers with the same base, we can add their exponents. And coincidentally, and they derive from each other, so it kind of makes sense, log base A of m times n, so again we're multiplying, produces the following relationship. Log base A of m plus log base A of n. So again, notice that all the base numbers, or in this case letters, remain the same. And these properties are related to each other in that when you're multiplying the two, the m and the n, you end up being able to to add them up. So for exponent properties, we condensed it. For log properties, they kind of expand in a sense. And we might need that as we're working with problems moving forward. Also note that you can move backwards or forwards with these properties, meaning you can go from log base A m times n to splitting them up, or you can start with addition and condense them. So be aware that you can use the properties either way. So moving on, we've got the quotient rule where we had, again, the same base, A, and when they're divided, you can subtract their exponents. And you can probably guess what the next one will be. We've got log base A of m divided by n, again, looking very similar to the exponent property. And you guessed it, we're going to go ahead and subtract those. So split them up and use subtraction. So there's a lot of relationships going on between the log properties and the exponent property. So be very aware of those. With the next property, we know that any number to the 0 power, and let me make sure that I'm denoting all of our base numbers here. Any number to the 0 power is equal to 1. Well, the same applies for logarithms, except this time, any base number, log base A of 1, will always be 0. And again, that refers back to this first property up here, where a to the m equals n. You're looking for exponents that produce the letter n. In this case, we're looking for exponents that will produce 1, and the only exponent that we know of that will produce 1 is 0. So be aware of this one. This is a good property to have at your disposal. Another property that becomes very important is this one. And again, this is coming from the idea of if I have a base letter A, when it's raised to the 1 power, it's going to equal itself, kind of like an identity. So you'll see this often also. This one is very, very important when we're trying to simplify equations utilizing log. So make sure that you have this one at your disposal. And finally, we have two more log properties that don't necessarily relate to any exponent properties that we've learned in the past. So I'm going to leave these two boxes empty. And I'm going to help you fill in those last two log properties that we need to know of for right now. And those are the following. First, we've got log base a of m to the r power. So when we have a logarithm that is raised to an exponent, and that could apply to either the m or the entire logarithm itself, it just so happens that we were able to prove that r can actually drop in front and become a coefficient of this log equation. So if I were to rewrite that, I can now write r times log base a of m. Okay, and again, this is a property that's going to come in handy as we're trying to eliminate exponents to begin with so we can solve problems or simplify problems. So know this one. And finally, we need our change of base formula. Okay, and the change of base formula, and all these are coming from section 5.5 of your textbook in case you want to check that out and see how they derived some of these. But this is our change of base formula. And this is another one that's going to be very important, especially because of the following reasons. Your calculators only have log or ln. So here's my quick sketch of a calculator. Okay, and you've got all these buttons on there, and most calculators, including the calculator you find on your iPhone, you actually have logarithms. You just gotta turn the iPhone on its side. Okay, you have logs there. But the buttons that you're offered in both your iPhone and most calculators is a button that says log. I believe on the iPhone it says log base 10. Okay, and you also have a button that says ln. Same over here in the iPhone or regular calculator. And so both of these log buttons are of base 10. And remember, in the last video, we talked about that being pretty typical. The ln refers to log of base e, which again was an irrational number that we talked about in the last video. So if I'm trying to solve an equation or simplify a log function, for example, log base 3 of 5, I don't have log base 3 on my calculator, which is a problem, because how am I supposed to punch this into the calculator if I can't write the base 3? Now, occasionally some really fancy calculators will have something like this, where you can type in your own base and then give the 5 on there when you're plugging it into your calculator, but most of us don't have that. So we need something else. We need something that's going to allow us either to simplify more easily or to use our calculator to solve. And so some really smart person out there created the change of base formula. And the change of base formula looks like this. If I've got log base a of m, I can actually choose my own base. I'll call it b. So log base b of m divided by log base b of a. So notice that I split up m and a, and I set them in their own personal log functions, this time with the base b that I've chosen. Okay, so in our example over here, instead of log base 3 of 5 now, I can split the 3 and the 5 up. Log 5 over log 3. And I have options. I can leave it like this and thus assume that the log is base 10. I can change it to be ln because perhaps I'm working with population, so ln makes a little more sense to use. It depends on the problem. I could also, well, I guess that's pretty much it. I could also choose any number that I want. For example, I could do log base 5. Maybe I wanted to try canceling something out. Maybe I wanted it to match another logarithm that I'm working with so I can cancel those kinds of things out. So really it depends what you need the base to look like, and you have the power to change that base using this change of base formula. Okay, so that's another one that's going to come up as we work through these problems. And so to recap again, our base numbers, or in this case letters, often are coming out the same, so keep an eye on those. We've got these two extra log properties here at the bottom, and we're going to be able to use these to solve some of our problems in our book, in ALEX, in your upcoming end of unit, and then any other situations you might run into, either real life, real situation, or classroom situation. You'll now have your log properties added into your math toolbox. Okay, and again, as we move forward, remember that exponents and logs, they're inverses of each other. So just like in Algebra 1, when you were practicing with multiplication property of equality, division property of equality, and again, we talked about this in the last video, being able to use those things back and forth and apply them to both sides of your equation is pretty much what we're doing again now, except that we've got a few more complicated properties to use. Okay, and I think that as we work through these, the biggest roadblock that we're going to run into, I guess, is going to be trying to figure out when to use these properties. So we were able to meet on Zoom today, and a lot of us had no problems understanding the properties, but the issues came up when we didn't know when to use which property, which direction should we go in order to get the right answer. So we're going to do a few examples together now, because after these properties, that's it. That's all you need to know about properties of logarithms. Let's do some examples together so that you have a better handle of some strategies and how we can progress in solving different log equations. Okay, so I'm going to start by accessing your textbook, and I'm looking at page 315, and I'm going to do some practice problems from there with you. Okay, so you might want to have a calculator ready. Also, just a suggestion, these log and exponent properties might be something you want to write down on some sort of reference sheet for yourself. On your test, I am not expecting you to memorize these. I'm not expecting you to not have them as a resource for yourself. Write them down on a sheet of paper and have them next to you while you're taking the test. The challenge isn't memorizing the properties. The challenge for our class is being able to use the properties. And so I don't want memorizing to be an issue. Don't worry about memorizing them. Worry about learning how to use them. Okay? So once again, we are looking in our textbook, and we are looking at page 315. Again, that's section 5.5, properties of logarithms. And we're going to start with problem 20. Okay, and problem 20 looks like this. We've got log base 8 of 16 minus log base 8 of 2. So we've got a few options here, and there isn't just one way to solve this thing. For example, maybe you see log 8 and you think instantly, we need a change of base here. We need to change the base so that it's something I can plug into my calculator. Now, if you're following along with your textbook, the instructions for number 20 say not to use a calculator. So we're going to do our best not to use a calculator and try to rely on our log properties to solve this and find the exact value as our answer. So we could go the change of base route. But it might make things a little more complicated. For example, and it's not wrong, we can do log 16 over log of 8. That's following the change of base rule, okay, right here. And I can subtract log of 2 over log of 8. Okay, and we have the same denominator, which is nice. It means we can start combining things. We can do something like log 16 minus log 2 all over log 8. But we end up stuck again because we still have this minus sign. So again, if you go the change of base route, you're not incorrect, but it's not really helping us simplify. If anything, it might make you a little more stressed out now, seeing all the extra logs. So let's take a different route. And if you remember when we were going through properties, I mentioned that properties are allowed to go right to left and left to right. So in other words, I see a minus sign here, and my instinct tells me to look at the minus sign in my properties. I do have a property that utilizes a minus sign. Okay, and so I can go the opposite direction for that. So I can move from right to left this time and simplify or condense this log number sentence, this expression. Okay, so notice that in my property with the minus sign, all my A's match. So I'm just going to go ahead and condense this thing. And this time, again, I'm focused on this base number here. I need the same base here, and that is base 8. So what's happening when we subtract two logs, right? And if you remember your exponent properties, when exponents are being subtracted, that meant there was some division happening before that, before we tried simplifying. And so we're going to do the same thing. And again, just to kind of keep us on track, I'm focused on this property right now, okay? So instead of having 16 minus 2, I'm going to go ahead and set 16 divided by 2. And again, I just took the parts from the log properties. In this case, 16 represents m in the property, 2 represents n in the property, and my property simplifies itself by setting m over n. And so I did the same thing here. And lucky for us, since our book says not to use a calculator, these things have to simplify down to something nice, and it does. When I simplify what's in my parentheses, 16 divided by 2 is 8. And so now I can look at another one of my properties, because I notice that my base is now equal to this number. That looks to me like that property. And so my final answer is 1. All that work so we can get an answer of 1. Okay, and so the goal here is to be able to pretty much puzzle out how to simplify these expressions in the best way possible. Let's try another example together. Here's our next example, same textbook page. This time we're looking at number 24. And we've got log base 3 of 8 times log base 8 of 9. And so we might be wondering, again, where do we even start, right? And one thing that we tried earlier today in Zoom is to do something like that, because we see 8s and it's nice to cancel them, especially when one's on the top and one looks like it's at the bottom. But again, we're limited to very strict rules when we're working with math. We can take any path we want, but we still got to follow the rules. So unfortunately, canceling out 8s like that is not a rule that we're allowed to utilize. That's something that we haven't proven. And so since it hasn't been proven, we can't use that rule. And so we might be looking at our log properties now and thinking, okay, where do I see, the last time we looked for the subtraction, and we saw it in this third property here. But we don't have subtraction this time. We've got multiplication of 2 logarithms. And as I look through my properties, I don't really see anything that will help us simplify when we've got 2 logarithms being multiplied with each other. And so when I'm stuck, sometimes the best thing to do is try out our change of base formula. See if anything will cancel itself out. So I'm going to go ahead and use my change of base formula, and I'm going to use base 10. And I'm only choosing base 10 because it's the generic base to use. You know, it's the typical logarithmic base. Yes, it's one using calculator, but we're not allowed to use the calculator for these ones according to our book. So we're gonna follow their instructions. But I'm gonna go ahead and go with 10 because it's typical, and I'm not gonna write 10 again because it's conventional not to write it. You don't have to write 10. If you do, you're not wrong, but it just usually isn't written. And I want to make sure that everybody watching is accustomed to the fact that if I don't write a base, it means it's automatically base 10 if it says log. And just as a quick reminder over here, remember that if it says ln, that means the base is e. Okay, that means log base e. But I'm not using e for right now. I'm just going to stick with log, and I'm going to change the base for both log functions. So just to make sure we're on the same page here, log base 3 of 8, I used the change of base formula, and then log base 8 of 9, I used the change of base formula. And so, just as you might have expected or suspected, our book makes it so that things come out really nice, and lucky for us, we get this awesome opportunity to cancel out log 8. Now I mentioned we couldn't cancel at the beginning because those logs were separated by multiplication. But this time you have a whole log function that you can cancel out with another one. So this type of canceling is okay. This is the same as when you cross-cancel fractions and things like that. This is good. This we're allowed to do, and so we can continue to use those properties with logarithms. So all your properties that you learned before, those still apply. We just have new ones to add to those. Okay, so now I can continue trying to simplify this. I've got log 9 over log 3. And we might be a little stuck here because, I mean, it's very tempting to divide, to do 9 divided by 3, but we can't because 9 and 3 are part of the log function. It's kind of like when we were doing things with sine and cosine. You can't just rip those numbers out of the sine and cosine function. It's part of that function. And in this situation, 9 is part of log in the numerator and 3 is part of log in the denominator. And so we can't just, start canceling things out while they're inside the logarithm. Whole logarithms are fine, like we did up here. But when they're separated, and we can't really cancel things out there. So perhaps it would help for me to go the opposite direction of the change of base formula, because I see that there's some relation with 9 and 3. I know those two things are related to each other. I've seen them tons of times when I work with exponents. Specifically, I know, and I might want to write this for myself off to the side, we know that 3 squared equals 9. So this might come in handy later. But I can't do anything with it now because these two numbers are separated into two separate logs. So let's combine them. We know that they both have the same base, again, base 10, right? That imaginary base 10 there. Let's combine them back. So in other words, I'm taking my change of base and I'm going backwards. I'm removing the base 10 that I used at the beginning because now I've got one fraction, so it might be nice to simplify it a little bit. And notice that m is the 9, and a is represented by 3 in this equation, or this expression. So so now our base a is a 3, and our m is a 9. Okay, so just to recap, and let me try and stay consistent with colors here. I had a base b, in this case we used 10, and I decided we're getting rid of that because we want it to look a little nicer. We want to eliminate some things. We know 3 squared equals 9, so if we can start condensing this thing again, now that we canceled out log 8, it might be better for us as we try to solve. Another thing we noticed is that 9 is our m, and so I write it next to my log. And finally, hopefully we see that 3 is a, and we always use that for our base number. And so now we have log base 3 of a. And so it's looking a little more simple, but as we continue on, let me get rid of some of these. Well, I'll leave the colors up for now. As we continue on, and I'm just going to set this, okay, so as we continue, and I'm going to scoot this up just a bit so we can continue working and we have room. Again, let's take this back to the information that we know, which is that 3 squared equals 9. So I'm going to go ahead and replace 9 with our 3 squared. Okay, because we know that 9 is equal to 3 squared. And now you might see, okay, when we see a log with exponents, our brain should immediately go to this property, which allows us to drop that exponent down in front as a coefficient. I can take this 2 and I can plop it right here in front. And so I end up with 2 times log base 3 of 3. And again, we see a log property. Okay, this one had all sorts of log properties going on. We had this property here, which says when this base number and the main number are both a, that whole thing equals 1. And so I end up with 2 times 1. And you guys might be skipping this step eventually because so many of you do good mental math. And my answer is 2. Okay, so all these log properties, just to prove that this expression simplifies down to the number 2. So if this is kind of, if this information is a little much for you, right now might be a good time to take a break. Maybe even rewind the video so you can see the beginning of 24 and watch through it again. See if you can guess which properties we need before we use them. And really figuring out when to use which property is going to be key in being able to solve these problems. So before I end this video, I do want to go over one more problem from your textbook that uses variables. So notice we haven't used any variables yet. I want to go over one more problem where we use variables, just so you can be prepared to see those in your Alex homework. Okay, so now we're going to look a little further in your book. Actually, we're looking at section 5.6, and this is on page 320, example 4, and they want us to solve for x. Okay, and actually, I take it back. We're going to do this example and one more that's a little more complicated, but here's a basic example of trying to solve a logarithmic equation, or in this case, an exponential equation with variables. So if you remember, exponentials, their inverse are logarithmic. And so just like with multiplication and division being inverses and addition and subtraction being inverses, we're going to use the two to kind of eliminate the other. So in other words, since I've got 2 to the x power, I'm going to go ahead and log both sides so that I can get rid of x in the exponent. Because having x in the exponent, besides graphing, it's a little hard to determine what those were. In the past, for example, if I had 2 to the x equals 8, that you can solve, right? Because you know that 2 to the x equals 2 cubed for 8, and x equals 3. So in not the last video, but the video prior about using exponential properties, that was easy. But now with the implementation of 5, and you might be thinking, well, 2 to the what power gives me 5, right? And so that's where we're running into a problem with exponents. With the ones from the prior video, yeah, we could solve them because they were nice numbers. But now that they're not nice numbers, we're kind of stuck. And that's why logs become very important when we're trying to solve these types of equations. You know, for what values of x will this exponential function equal 5? And so we're going to go ahead, and sure, you could graph it, but in this situation, we're going to go ahead and log both sides. So notice that just like with the properties of equality from Algebra 1, I'm still applying things to both sides of my equal sign. That whole rule still continues when I'm adding a log in there. If I'm using the properties, that's fine because those properties are equivalences. But right now, since I'm adding a log function on both sides, I'm adding a log function to one of the sides, I'm going to have to make sure I add it to the other. So now I've got log base 2 to the x power and log base 10 of 2 to the x power and log base 10 of 5. Okay. And we know we can still, of course, every time we see exponents, our goal was to get the exponent out of there. So I'm going to go ahead and drop it down into the front as a coefficient so that now I have x times log base 10 of 2 equals log base 10 of 5. Okay, so far so good. At least we got the x out of the exponent. We can probably solve this a little easier now. Hopefully you're seeing that this multiplication, inverse of multiplication is division. So I'm going to go ahead and divide both sides by log 2. At this point, you could plug log 2 into your calculator, but oftentimes when you plug in logarithms to your calculator, it starts to produce these really long, crazy looking decimals. So our goal right now is going to be to get it as simple as possible and then drop it into our calculator. Okay, so continuing on, I've got x equals log 5 over log 2. I suppose then at this point, you can go ahead and put it into your calculator. Be careful about rounding. Try to, if you don't have a calculator where you can plug in the whole number sentence, so for example, you might write log 5 divided by log 2. If you have a calculator that can do that, like the graphing calculators, that's good. But if you don't, try to just round to 3 decimal places. So I've got my calculator here. And the top one, if I turn, I'm using my iPhone, so I'm going to turn my iPhone on its side, like I mentioned, and I'm going to type in a 5, and then I'm going to hit log base 10. And that gives me 0.6989, so I'm going to round up. And then log of 2, again, I'm going to type 2 into my calculator and then hit the log base 10 button. And that gives me 0.301. And when I divide those two in my calculator, I end up with 2.322. So there's my answer. And if you're wondering what that answer means, ultimately it means that 2 to the 2.322 power equals 5. Okay, so again, what does our answer mean? It means that if I were to graph this function, at 2.322, we are at a y value of 5. Okay, so I'm actually going to stop here. There is a situation where we have quadratics when we're trying to solve, but I don't plan to put that on your test. Just know that they exist. Know that it is possible to get 2 answers for x, and ultimately you'd have to decide, you know, negative ones don't really make sense for logarithms because log functions never go into negative x. So if ever you get an answer for x where your answer is negative, I would just like to, and it's a good error check, you know, even for this problem, I'd just like to remind you that for log functions look like that. Unless it's been transformed around the coordinate plane. So if you've just got a basic log function, then just be aware that we don't have negative values for x. So really understand what function you're using so that you're paying attention to how reasonable your answers are. A lot of you were talking about the Peterson activity and how some answers seemed reasonable and other answers did not seem reasonable. Knowing how reasonable an answer seems is actually a really powerful tool to have as you're trying to find answers as you work through these. So keep an eye out for that. As we saw here, you can always check, okay? You can always check your work. If you have a calculator, I can always type in 2 to the 2.322 and see how close it gets to 5. It should be pretty close. So work through these carefully. Rely on your properties, trust your properties, and do the practice. It's not going to feel natural until you start doing the practice problems. So if you're kind of iffy at first, feel free to ask questions. It's totally natural and totally normal if you're feeling like you're not sure where to go with these problems. Try your best. One of our classmates in Schoology mentioned, if you don't just try and answer, then we can't have a discussion, which I thought was an awesome point. So that's totally true. Just try something, you know, try change of base and see if anything happens. If nothing happens, you start over. It's not the end of the world to start a problem over. So please take the time, go into Alex and complete the homework on properties of logarithms. Just a heads up for my pre-calculus classes, on Friday, you will be having a practice end of unit. It will be posted on Alex. It'll be about 10 problems, and it's going to emulate what you will be seeing on the end of unit next Wednesday. So if you didn't know there was an end of unit next Wednesday, it means that you weren't checking the calendar. We actually moved it from this Wednesday, so we don't want to rush through these things. We want to make sure we understand. So it got moved from this Wednesday to next Wednesday. And we agreed today in Zoom that I would make myself available Friday at noon. So the same usual pre-calculus Zoom link, you know where to find us. You have those links on your Schoology page. Hop into Zoom if you have any questions on your practice end of unit or on this material, and we would all be happy to help each other navigate those so that we are better prepared for our end of unit on Wednesday. That's May 6th. Okay, so thanks for tuning in as always. I really appreciate the feedback that you've given me on the videos. I continue to hope that they are helpful and that they're helping you navigate all of this work in our giant pre-calculus book. Stay safe out there, and I hope to see many of you on Friday so that you can get a little extra support if you need it. So we'll be there to, again, support each other in our little Mrs. Martin math community. So anyway, thanks for watching, and I'll see you in the next video. Bye-bye, everyone.